In this video, I want to show you different methods for finding limit of sequences that are in the form of rational expression, like this example here, and more complicated examples. I will show you 4 different methods for finding limit of these sequences. Some of these methods are fast and easy. Some of these methods are more general, and you can apply them for other examples. The first method that I want to show you for finding limit of this sequence is very effective and very fast method that you can find limit of rational expressions like this example really very fast. You know that when we talk about limit of a sequence, we want to find limit of the sequence at infinity. So here we want to find limit of 5n over n to the 2 plus 9 as n approaches infinity. In this method, we keep the dominant term in numerator and the dominant term in denominator. What is a dominant term? The term with the highest degree, the term that is significantly bigger than the other terms. So we ignore, we delete, we cancel other terms, just we keep the dominant term or terms that are dominant in numerator or in denominator. Look at the numerator. We have only one term, so we have 5n. In denominator, we have 2 terms, n to the 2 and 9. Which one between these 2 terms is significant? Which one is more important? Which one is bigger? N to the 2. Because n to the 2, n approaches infinity, but 9 is a constant, so n to the 2 is important. We keep this and we ignore 9 completely. Now simplify this. 5n over n to the 2 is 5 over n. So we have a limit of 5 over n as n approaches infinity. We know that limit of a number, in numerator we have a number, over something that approaches infinity is 0. Any number over infinity approaches 0. So the limit of this sequence is 0. So this given sequence approaches 0. So this sequence is a convergent sequence and it converges 0. So this is our first method for finding the limit of this sequence. Keep the dominant terms, the terms that are bigger, significantly bigger than the other term. Basically, the dominant term is a term that the other terms that we ignore them are nothing compared to the dominant term. For that reason, we can ignore those terms and we can just keep the dominant term. Now let me show you another method for finding this limit. The second method for finding this limit is using L'Hopital rule. Remember, we can use L'Hopital rule, which was a method for finding limits of functions. We can use L'Hopital rule in 2 cases. When if we have a limit in the form of 0 over 0 or infinity over infinity. Usually in sequences, we have infinity over infinity. So we can use L'Hopital rule for finding limit of sequences. But attention, don't make this mistake to write limit n approaches infinity and write the expression. No. When you want to use L'Hopital rule, make the variable, change the variable name from n to x. So basically you have to write it this way. For finding limit of this sequence, we are going to find limit of 5x over x to the 2 plus 9 as x approaches infinity. Yes, this is just a change in the name of the variable. Maybe you think by yourself, what is the difference? This is the same thing. The thing is that when n is integer, in the sequence, n is an integer. N cannot be decimal, n is an integer. And when the variable is integer, you cannot take derivative from that. Mathematically, it's wrong, completely wrong, to take derivative of something like 5n or n to the 2. So, to write your solution in the right way, change the variable name. It's very simple. Change the variable name to x, then start using L'Hopital rule. Based on L'Hopital rule, if you remember, for finding a limit which is in the form of infinity over infinity, we take derivative of numerator. What is the derivative of numerator? 5. What is the derivative of denominator? 2x. Because the derivative of x to the 2 is 2x. And the derivative of a constant like 9 is 0. So derivative of numerator is 5, derivative of denominator is 2x as x approaches infinity. And now if you pay attention, 5 over infinity, a constant over something that approaches infinity is 0. So these two answers are of course the same. So L'Hopital rule is another way for finding limit of sequences. Of course, if it is possible, and it is possible when we have infinity over infinity, then we can use L'Hopital rule for finding the limit of the given sequence. And of course, we use L'Hopital rule when finding derivative is not too complicated. If finding derivative of numerator or denominator is impossible or very challenging, maybe it's better to ignore using L'Hopital rule. For example, suppose in the denominator you have factorial. Can we take derivative of factorial? No. So we cannot apply L'Hopital rule for such examples. We need to have fraction first of all, and we need to be able to find derivative, like this example. Now let me show you another method for finding limit of this sequence. So this is the third method for finding limit of this sequence. If you remember limit of functions at infinity, for finding limit of functions at infinity that are in the rational form, so suppose we have an expression in numerator, an expression in denominator. For finding these type of limits, if you remember from functions, we divide numerator and denominator, every term of numerator and every term of denominator by the highest degree of denominator. This was the method for limit of functions at infinity, if you remember. Divide every term of numerator and every term of denominator by highest degree of denominator. So here, if we want to apply this method here, for finding this limit of 5n over n to the 2 plus 9, we have to look at the denominator. And as you can see, the highest degree of denominator is n to the 2. So we divide every term of numerator and every term of denominator by n to the 2. Like this. Now we start simplifying these expressions if it is possible. In numerator we have 5n over n to the 2. So if we simplify that, we have 5 over n. In denominator, n to the 2 over n to the 2 is 1 plus 9 over n to the 2 is 9 over n to the 2. We cannot do anything with that. Now attention, because n approaches infinity, the limit of 5 over n is 0, because a number over infinity is 0. So the limit of this part is also 0. So this limit is equal to 0 over 1 plus 0. So 0 over 1 plus 0. And this equals to 0. So the limit of this expression is equal to 0. As we can see, all of these answers in 3 different methods are the same. They should be the same. This is another way that you can find the limit of this sequence. Now, let me show you a fourth method. Maybe you wonder by yourself, you ask by yourself, why we have to learn different methods? Because some of these methods work better in some situations, in some examples. So learn different techniques and start applying them when they work effectively. Of course, this technique is very effective, and compared to this method is faster. But attention, in this method you show your work, but here basically this is not really mathematical way. It works, you can get the answer, but maybe this is not a completely mathematical method. Which we say in this method, what we say? We say just keep the dominant terms and ignore these terms. And as you can see here, also at the end we ignore this because it becomes at the end 0. But here we do it in a faster way. And now let's talk about the fourth method. In the fourth method, I want to remind you something again from limit of functions. So let me rewrite the given sequence here. The sequence was this 5n over n to the 2 plus 9. But before that, let me remind you something from limit of functions at infinity. If you remember, when we had polynomial, any polynomial like x to the 2 minus 4x plus 3 over another polynomial, a rational expression basically, if you remember this from functions. So whenever we have a rational expression like this expression, for finding the limit of the rational expression, we had this rule that if the degree of the polynomial numerator is bigger than the degree of the denominator, then the limit is either positive or negative infinity or negative infinity. If the degree is the same between numerator and denominator, then the degree would be a number, which that number is the ratio of the leading coefficient of the numerator over the leading coefficient of the denominator. I will explain this in a moment. Let me finish this, then I will explain this in detail to you. At the end, if the degree of numerator is less than the degree of denominator, then the limit is 0. In our example here, if we want to use this technique, look at the numerator, 5n. Look at the denominator, n to the 2 plus 9. The degree of numerator is 1. In denominator, we have degree 2. So the degree of the denominator is bigger than numerator, or the degree of numerator is less than the degree of denominator. And when this happens, the limit of the sequence is, limit of the function and limit of the sequence is 0. So by this technique, you do basically nothing. Just you need to remember this. And if you remember this, you can find the limit of the rational expression right away. So the limit is 0 because the degree of numerator is less than the degree of denominator. Let me show you some examples of the other cases and how we can use this technique to find limit of sequences really easily. For example, suppose we have this. an is given n to the 2 minus 4n plus 7 divided by 5n to the 2 plus n plus 10. Based on this, what is the limit of this sequence? What is the limit of an? Let me name this bn. So what is the limit of bn when n approaches infinity? Degree of numerator is 2. Degree of denominator is 2. So this is this case. So now look at the leading coefficient. What is coefficient of n to the 2 here? 1. What is coefficient of n to the 2 here? 5. So a is 1, b is 5. So the limit of this sequence is 1 over 5. And again, you can find limit of this sequence with the other methods that I have shown you so far. Method 1, method 2, method 3. Using L'Hopital, using keeping the dominant term, using dividing the numerator and denominator by highest degree. You can use those methods, but this method is faster, at least for these examples. Let me show you an example from this case basically. For this case, consider this sequence Cn, consider the sequence Cn given by, for example, 5n to the 3 plus n plus 1 over 2n plus 5, for example. What is the limit of this sequence? When n approaches this infinity, the limit of this sequence is infinity. Why it is positive infinity? How we can figure out is it positive infinity or negative infinity? First of all, we note that the degree of numerator is bigger than the denominator, so it's obvious that the answer is infinity. But it can be positive or negative infinity. To figure out that, focus on these two terms because these are important. These are nothing compared to these two. Now look at the coefficients. The coefficient of the top is positive. Coefficient of this one is positive. So positive over positive is positive. But let's say this example was negative 5n to the 3. Then the limit of this sequence would be negative infinity. Because negative 5 divided by 2 would be negative at the end. So the limit is negative infinity. Now let's say, what about if we had a negative also here? Then when we consider these two, when we divide negative 5 by negative 2, negative with negative cancel, this would be positive. So depending to the sign of this number and sign of the leading coefficient, these are leading coefficients, depending on these two, we can figure out is it infinity or negative infinity. So this is the fourth method for finding limit of a sequence when it is like a rational expressions. Now look at these examples. These two examples are also in the rational expression form. So we can use this last technique, the fourth method, for finding limit of these sequences right away without thinking. For example, what is the limit of this sequence when n approaches infinity? The limit of this sequence when n approaches infinity is 2, because degree of numerator is the same as degree of denominator. When the degrees are the same, the limit is the ratio of these coefficients, 2 over 1, so the limit is 2. You can use other methods. You can use L'Hopital rule to find limit of this, but you have to apply L'Hopital rule 3 times to find this answer. You can divide every term of the top, every term of the bottom by highest degree of the bottom, which is n to the 3. Then you can find the limit. This is another way. You can use the first method that I taught you in this video. What was that method? Ignore smaller terms. Keep these two. 2n to the 3 over n to the 3 is the same answer, 2. So this method is also very effective, as you can see. So the limit of this sequence is 2. Look at the next example. The degree of numerator is bigger than the degree of denominator. So the limit of this sequence should be infinity. But is it infinity or negative infinity? What do you think? Limit of this sequence when n approaches infinity is negative infinity. And the reason is that this coefficient is negative, this coefficient is positive, negative over positive is negative. So the limit is negative infinity because the degree of numerator is bigger than the denominator, and the coefficients gives you a negative. You can use L'Hopital rule to find this limit. You can use other methods, like dividing numerator and denominator by highest degree of denominator, which is n. So you can divide every term in numerator and every term in denominator by n. It takes some algebra to do the question and simplify and get the answer, but it works. And if you use first method that we learned in this video, what was the first method again? Keep the dominant term. What is the dominant term in numerator? This term. What is the dominant term in denominator? 4n. Let me show you how it works for this question. Suppose we want to find the limit of this sequence. So we want to find limit of this sequence with the first method. In the first method, if you remember, we just keep the dominant terms, the terms with the highest degree. So this over this. Simplify this a little. N to the 2 with n cancels and we have negative 3n over 4. N approaches infinity. Now n goes to infinity. So this n goes to infinity and we multiply this infinity by a negative 3/4. Because of this negative, the answer would be negative infinity. When you multiply a number that is positive by infinity, it's positive infinity. But if you multiply positive infinity by a negative number, the answer would be negative infinity. So the answer is the same, as you can see. Now look at these two examples here. 2 radical n over radical n plus 3, n to the 2 over radical n to the 3 plus 4n. These are not really rational expressions because maybe you think by yourself we have a radical. Yes, you are right. But attention, again we have n with different powers in numerator and denominator, so we can consider them as rational functions. basically, if you think for a moment, you can write this as 2n to the power of 1/2 over n to the power of 1/2 plus 3. So if you think this way, you can still use the methods that you have learned so far for finding limit of this sequence. If we want to use the fourth method, which was the fourth method? The method which was based on the degrees. What is the degree of numerator? N to the 1/2. The degree of denominator is also n to the 1/2. So the limit of this sequence based on that method is the ratio of the coefficients. So the limit of this sequence, limit n approaches infinity of this sequence, is equal to leading coefficient over leading coefficient, 2 over 1 or 2. This is one way, which is based on the fourth method. The other method that we can use for finding limit of this sequence is the first method. What was the first method? Keep the dominant term. What is the dominant term in the top? Just we have one term, so whatever it is dominant. But in the bottom, radical n is important. We ignore 3. N approaches infinity. Simplify this with this, 2. Same answer. Also, you can use L'Hopital rule to find this limit, but you have to take derivative. So these methods are easier compared to L'Hopital. Another way is to divide numerator and denominator by highest degree of denominator. Let me show you that method as well very fast here. Limit n approaches infinity. So we divide every term in the top and every term in the bottom by radical n, because radical n is the most important term in denominator. So we divide every term in numerator and every term in denominator by highest degree of denominator. So we have this. What is this? 2. What is this? 1. What about this? 3 over radical n when n approaches infinity is 0, because any number over infinity is 0. So we have 2 over 1. 2. The answer is the same. Now look at the next example. What about this? If you attention, the degree of numerator is 2, n to the 2. What is the degree of denominator? What is the highest term, highest degree of the denominator? If you attention, this is like nothing compared to this. So here, basically, the highest degree of denominator is n to the 3 over 2. Don't make this mistake to say n to the 3. No, it is under square root. So this is like n to the 3 over 2. So now, based on the fourth method, which was based on the degrees, what is the limit of this? Limit of numerator is 2. Limit of the denominator is 3 over 2 or 1.5. Limit of this sequence is infinity, because the degree of numerator is bigger than the degree of denominator. So immediately we say limit n approaches infinity of this sequence is infinity. Again, because the degree of this is 2, the degree of denominator is 3 over 2. So the degree of the top is bigger than the bottom, so infinity. Why it is positive infinity? This coefficient is positive, here is 1, so everything is positive, so it makes sense that the limit is infinity, not negative infinity. But if we had, let's say, negative 4 here, then the limit is negative infinity. The other way that you can find this limit is to use the first method. What was the first method? Keeping the dominant terms in numerator and denominator. In that method, we have n2 over radical n3. We ignore this. Then we have limit n2 over n to the 3 over 2. Because here we have a division, we subtract the powers. 2 minus 3 over 2, 2 minus 3 over 2 would be 1/2. So we have limit of radical n when n approaches infinity. N to the 1/2 is radical n. And limit of radical n when n approaches infinity is infinity, because radical infinity is also infinity. A square root of infinity is infinity. And it's the same answer. The other way for finding limit of this sequence is using L'Hopital. But using L'Hopital is not really a good idea, because you have to take derivative of radical n to the 3 plus 4n, then you get another radical. It makes it so complicated, and it's possible that you cannot find the answer at all. So It's not a good idea to use L'Hopital, at least for this question. And the other way is to divide numerator and denominator by highest degree of denominator. If you want to use that way, don't forget, the highest degree of denominator is radical n to the 3, or n to the 3 over 2. Now look at this example, cosine of n pi over n plus 4. You should not be confused by cosine. Notice the inside of the bracket. It's very simple expression, n pi over n plus 4. And we know that how to find limit of n pi over n plus 4. We know 4 different methods for finding limit of the inside of the bracket. For example, if we just keep the dominant terms, n pi over n would be pi. So the limit of inside of the bracket is pi. Another way, the degree of numerator is the same as denominator, so we just keep the ratio of the coefficient pi over 1. So as you can see, there are different ways to find the limit of the inside of the bracket. And just after we find the limit of the inside, just take cosine from that, and that's the answer of this limit. Let me show you. So for finding limit of this sequence, limit n approaches infinity, of cosine of n pi over n plus 4, for finding this limit, because we have no n here, we move limit to the inside. We focus basically on the inside. You don't need to write it this way, but it's good to write it this way. So we say for finding this limit, we focus on the inside. So we focus on limit of n pi over n plus 4. Now, what is the limit of n pi over n plus 4? For finding this limit, you can use L'Hopital rule. You can use all the methods that we have learned so far. Limit of this expression is simply pi. For example, if you want to use the dominant term method, this is the dominant term, this is the dominant term, n pi over n is pi. This is one method. If you want to use L'Hopital rule for this, you can say limit of pi x, or x pi, the order really doesn't matter, over x plus 4 when x approaches infinity is based on the L'Hopital. We take derivative of the top, pi. What is the derivative of the bottom? 1. So it's pi. This is another way, which is based on the L'Hopital method. The other way, if you remember, the degree method. We look at the degree. The degree of the top is 1 because we have n to the 1. Degree of the bottom is n to the 1. When the degree is the same, the limit is a number. What is that number? The ratio. The ratio of what? Ratio of coefficient of n over coefficient of n. Here coefficient is 1. Here coefficient of n is pi. Pi over 1 or pi. Another way, divide every term of the numerator and every term of denominator by n. So you divide this by n, divide this by n, divide this by n, simplify, and you can get same answer. Cosine of pi is, what is cosine of pi? Negative 1. Because remember unit circle, pi is here, and the cosine at pi is negative 1. Because cosine is x-axis. What is x value at this point? Negative 1. What is sine of pi? 0, because the y value of this point is 0, but the cosine is negative 1. Now look at this example. I highly recommend you pause the video here, try this example by yourself, and then continue watching the video. The given sequence is e to the power of negative 2n over n to the 2 plus 1. Don't confuse yourself with exponential function. Focus on the exponent, because in the exponent we have n. E is just a constant. Focus on the exponent. You have negative 2n over n to the 2 plus 1. What is the limit of negative 2n over n to the 2 plus 1? The degree of numerator is less than the degree of denominator. When the degree of numerator is less than the degree of denominator, based on the fourth method that we have learned, the limit of this is 0. So, for finding the limit of e to the power of negative 2n over n to the 2 plus 1, when n approaches infinity, we focus at numerator. We focus at exponent, not numerator. We focus at the exponent. And we can bring limit to here. Because exponential function is a continuous function, so we can do this. Look at this. We have negative 2n over n to the 2 plus 1. In different ways, you can find this limit. If you want to use the fourth method, in the fourth method, we look at the degree. The degree of the top is 1. The degree of the bottom is 2. When the degree of the top is less than the bottom, the limit is 0. So this is e to the 0, and then the answer is 1. This is one way for finding this limit. If you want to use method 1, what was method 1 again? Method 1 was the method that was based on keeping the dominant term. What is the dominant term in the numerator? Negative 2n. In the bottom, we have n to the 2. Negative 2n over n to the 2 is negative 2 over n. And limit of this is 0 because we have a number over infinity. So this approaches 0. So based on this method also, we get e to the 0, which is 1. You can use also L'Hopital for finding the limit of this. If you write negative 2x over x to the 2 plus 1, then if you apply L'Hopital, when x approaches infinity, then you would have negative 2 over 2x, and this is obviously 0. And this is the third method, or L'Hopital method. So with the L'Hopital method also, we get e to the 0, 1. L'Hopital method. What about dividing every term of the top and every term of the bottom by highest degree of the bottom? Let me show you that method here, because it takes to do. I cannot do it here. So we have e to the negative 2n over n to the 2, n to the 2 over n to the 2 plus 1 over n to the 2. This is 1. This is negative 2 over n. When n approaches infinity, this is 0. This is 0. And because numerator is 0, 0 over 1, because in the denominator we have this 1, all of this is 0. So we have e to the 0, and e to the 0 is 1. Now look at this example. The given sequence is cube root of 8n to the 2 plus 1 over n to the 2 plus 4. Again, as you can see, the important part of this sequence is inside of a cube root. So focus on the inside. And you should be able now to find the limit of the inside right away with one of the methods that you have learned so far. The degree of numerator is the same as degree of denominator. So 8n to the 2 over n to the 2 is the thing that is important. And so the limit of the inside of the cube root should be 8. Let me show you how we can find the limit of an when n approaches infinity. If we want to use the dominant term method, we keep 8n to the 2 over n to the 2, and this equals cube root of 8. N to the 2 with n to the 2 cancels. Attention, we ignore this because we keep the dominant terms. 8n to the 2 over n to the 2 is 8, so we have this. And cube root of 8 is 2. Attention, when in the expression we don't have any n, you don't need to write the limit here, because this is a constant. So the limit of this sequence is 2. If we want to use the degree method, then the limit would be cube root of, we focus on the numerator, 8n to the 2, the degree that is important is this, and the degree of denominator is n to the 2. So the degree is the same. So based on the degree method, because the degree of numerator and denominator is the same, so the limit is the ratio of the coefficient, 8 over 1. Attention, here the coefficient is 1. And 8 over 1 is 8, cube root of 8 is 2. So the limit is 2. And attention, you can use L'Hopital rule for this example also. But these methods are easier compared to the L'Hopital rule. If you want to use L'Hopital rule for finding the limit of cube root of 8x to the 2 plus 1 over x to the 2 plus 4, you can do it this way. First you have to write cube root, then you move the limit to the inside, and x approaches infinity, of course. And you know that you have to change n to x. So we have this basically. Now we apply L'Hopital for this, because it doesn't make sense to take derivative of this, because in this form we don't have any fraction. We move the limit to the inside, then we use L'Hopital for finding limit of the inside. By taking derivative of the inside, we have limit x approaches infinity, cube root of. Now use L'Hopital, derivative of the top is, the limit should be inside. Why I wrote it this way? The limit is inside, so we have cube root of limit x approaches infinity 16x over 2x. This is the derivative of the top over the derivative of the bottom. 16x over 2x is 8, so it's cube root of 8 again, which is 2. And if you want to find limit of this given sequence with the dividing method, with dividing numerator and denominator by highest degree of denominator, you have to divide these terms inside this big cube root by n to the 2, and then you can use that method. Let me show you briefly here that method. Limit n approaches infinity. We want to divide every term of the top and every term of the bottom by highest degree of denominator, and highest degree of denominator is n to the 2. So we put cube root here, then we have 8n to the 2 over n to the 2 plus 1 over n to the 2 over n to the 2 over n to the 2 plus 4 over n to the 2. If you pay attention, this is 0, this is 0, because these are numbers over infinity. This is 8, 8, and this is 1. So this is cube root of 8 over 1 or 8, and the limit is 2. As we can see, you can use all the methods. But of course some of them are easier, and so it's better to use those methods for finding limit of sequences. Now look at this example. What is the limit of the sequence 3n to the 2 plus 1 over n to the 2 minus n plus 1 all raised to the power of 2 radical n over n plus 4? If you pay attention, we can find the limit of this bracket when n approaches infinity with the methods that we have learned, and also we can find the limit of the exponent also with the methods that we have learned. And if you pay attention, easily we can prove that this limit of this part is 3 and the limit of the exponent is 0, so the limit of this sequence is 1, because 3 to the 0 is 1. But let me show you all these in details. For finding limit of an when n approaches infinity, we want to find the limit of this expression to the power of 2 radical n over n plus 4. Let's focus on the inside. Let's focus on the inside of the bracket. Because the degree of numerator is the same as degree of denominator, we have seen several times things like this, and we know that in questions that the degree of numerator, the degree of denominator is the same, the limit of the sequence is the ratio of this coefficient to this coefficient. So the limit is 3 over 1. Or if you just keep the dominant terms, which are these two, 3n to the 2 over n to the 2 is 3. So we have 3 to the power of, now what is the limit of this? The limit of 2 radical n over n plus 4 when n approaches infinity is 0. Why this limit is 0? Because the degree of numerator, the degree of radical n is 1/2. Basically radical n is n to the 1/2, but the degree of the denominator is n to the 1. And remember, when the degree of numerator is less than denominator, it means that the denominator is the bigger term. So the limit of the fraction is 0. And 3 to the 0 is 1. Another way that you can show that the limit of this is 0 is to just keep the dominant term in numerator and denominator like this. Then if you simplify this, you have 2n to the 1/2 over n to the 1. If you subtract the powers, attention, the power of denominator is bigger. The power of numerator is 1/2, the power of denominator is 1. If you subtract the power, you have 2 over n to the power of 1 minus 1/2. This is like moving this to the denominator. What is this power? 1 minus 1/2 is 1/2. So we have 2 over n to the 1/2, and this is like 2 over radical n. And this should be obvious that the limit of this is 0. And also you can use L'Hopital rule for finding the limit of the exponent. So in different ways we can prove that the limit of the exponent is 0, so the limit is 3 to the 0, and the answer is 1. Now look at this example. What is the limit of the sequence arctangent of n to the 2 plus 1 over n to the 2 plus 9? If you pay attention, the expression inside the bracket is a rational expression, and we can find the limit of this easily. So for finding the limit of this sequence, limit of n approaches infinity of arctangent of n to the 2 plus 1 over n to the 2 plus 9. Because arctangent is a continuous function, we can move the limit to the inside. So we can focus on the inside. So we can write this as arctangent or tangent inverse of limit n approaches infinity n to the 2 plus 1 over n to the 2 plus 9. Now what is this limit? It should be obvious for you that this limit is 1, because if you remember, when the degree of numerator is the same as denominator, we look at the coefficients. Coefficient of n to the 2 is 1, the denominator is 1, 1 over 1 is 1. So this limit is 1, and so the limit of the sequence is equal to arctangent of 1. For finding arctangent of 1, you have to think it this way. What is the angle that its tangent is 1? This is the definition of arctangent, the tangent inverse. So now we are looking for an angle that its tangent is 1. And if you think about it, it's pi over 4. Tangent of pi over 4 is 1. And this is the answer of this limit. For finding limit of this part, you can use also quotient rule. You can use L'Hopital rule, not quotient rule, L'Hopital rule for finding this. Or you can use just dominant terms. n2 over n2 is also 1. Or you can use the other way, which was dividing numerator and denominator by highest degree of numerator. Highest degree of denominator. And if we divide every term in numerator and denominator by highest degree of denominator, which is n to the 2, then we can find this limit. Look at this example. What is the limit of the sequence n to the 3 cosine n over n to the 3 plus 2n plus 5 when n approaches infinity? The thing that makes this question a little difficult and a little tricky is that we have n to the 3 in numerator, but its coefficient is not a constant. It's not like 2n to the 3 or 3n to the 3. We have a n involved in the coefficient of n to the 3. The coefficient of n to the 3 is cosine n. And before we start talking about limit of this sequence, let me remind you, limit of cosine n or sine n when n approaches infinity does not exist. Because if you look at the graph of cosine or sine when n goes to infinity, if we go far to the right, this graph goes up and down forever. And it doesn't approach to a fixed value. It goes up to 1, then goes down to -1. It oscillates up and down forever. So cosine n or sine n, when n approaches infinity, the limit does not exist. Keep this in your head. Now let's focus on this question. We can see that the dominant term in the bottom, in the denominator, is n to the 3. And in numerator just we have one single term, and that term is n3 cosine n. So for finding this limit, if we want to use the dominant term method, we have this n to the 3 cosine n over n to the 3. If we cancel n to the 3, then we have this cosine n. And cosine n at infinity does not exist. So this sequence is not convergent, and this sequence is divergent. Another way for finding the limit of this sequence is to divide everything in the numerator and everything in denominator by highest degree of denominator. What is highest degree of denominator? N to the 3. So we divide the term in numerator by n to the 3. We divide everything in denominator by n to the 3. Then we have this basically. In numerator, if we simplify, n3 with n3 cancels and we have only cosine n. In denominator, we have n3 over n3 1. 2n over n to the 3 is a 2 over n to the 2 plus 5 over n to the 3. Because n approaches infinity, these are 0. And we have cosine n over 1. And we know that when we have cosine or sine of n, when n approaches infinity, the limit of this does not exist. And so the limit does not exist. The sequence is divergent. So this sequence converges basically to no number because this is divergent sequence. So the sequence diverges. In this video, I try to show you different type of examples, easy and hard examples of rational expressions, sequences in the form of rational expressions, sequences involving rational expressions, and I try to show you different methods for finding limit of these type of sequences. If you like this video, please subscribe in my channel and see you in the next videos.